Hello, everybody. Welcome to EEE 135 Renewable Energy Systems, where today we're going to talk about Chapter 8, Wind Turbine Control. So, last time we were talking about the inner workings of wind turbine and how to create or induce electric energy. Now we're going to talk about how to position it, control it to optimize that power output, right? So, wind turbines need to be controlled precisely 24 hours a day, 7 days a week for a few reasons. Number one, power output. We want to make sure we keep rated power going as much as possible so we can get the highest amount of money back from our investment. Remember, every time we produce a megawatt of power, we get paid from the power grid to do that. Okay. Number two is safety. We don't want the wind turbine to have an overspeed condition where we're turning faster than what is mechanically rated. You can end up damaging equipment, wearing out bearings, and it'll be a costly maneuver because at the end of the day, you're going to spend money to fix it. Okay. Not to mention, you're going to have a loss of generation time because you're taking things offline. Lastly, controls. We need to have some type of speed control to make sure that the wind turbine turns at a steady frequency that's acceptable to the equipment's design. We also want to make sure the wind turbine is facing in the correct direction to optimize the amount of power we get from the wind itself. Okay. Now, these wind turbines, you can characterize them by two different speed types. You have a constant speed wind turbine where the whole mechanical system wants to have a pretty steady frequency, and we have to change something to make sure that the wind power will change based on the wind speed itself, right? So something with the blades we're gonna have to do to make sure we have constant speed on the mechanical shaft. Another design is we could just let the mechanical speed vary up and down based on the wind speed, and we can fix it downstream on the electrical side. That works just as well. So these are two different types we're going to look at. Okay. Now, regardless of what we use, we need something called pitch control. Okay. So if we want to optimize the wind turbines, we need to make sure we can move these blades in a circular pattern to change the pitch. So we need some type of pitch control, right? So for wind optimization, the pitch needs to be controlled. This is accomplished by tilting the whole individual blade, and this changes the angle of attack. Remember, we talked about there's a critical angle of attack. We could increase it or decrease it to change the amount of power going to the wind turbine, which will then change the speed as well. Okay, this is called pitch control at the end of the day. So notice that image right here, you'll have some kind of mechanical system or electrical system like motors that will actually spin this blade plus or minus probably about 90 degrees to capture more or less of the wind power. Okay. And then you have the main body. It's also called the shell. It's just a fancy word to say the main body itself. This is where you have all the equipment installed inside. Okay. Now that we know that the blades can spin, there's one special condition called blade feathering. What we can do is we can make sure that the blades will be completely parallel with the wind flow. So that's what blade feathering does. Why do we want to do this? Well, remember from our previous section, if the blade is completely parallel with the wind, you're not going to have that high pressure on the top, low pressure on the bottom, the angle of attack, all that lift, all that goes to zero. You're not turning the wind blade anymore. It's literally kind of inert, right? So it's very useful when we want to stop producing power. Now, why we want to stop producing power? Maybe we want to lock the blades. We want to do maintenance. Notice that right here, you see the hatches open, so they're probably doing some maintenance. That's why they feathered the blade and locked everything in place. You don't want to mess with anything while it's turning because you're going to hurt yourself. Okay. So that's what pitch control is. Now, for the constant speed turbine, what we're going to look at is we have the wind turbine blades itself. We have a specific gearbox, a generator, and then we have a capacitor bank to kind of help with the power factor correction a little bit, and then we're going straight to the grid. Okay, so for a constant speed turbine, this mechanical linkage right here, the speed needs to be constant at all times so that the generator spins constantly so we keep 60 hertz output. Okay, So how often does the pitch need to be monitored for changes? Now, remember, there was no power electronics that fixed the frequency. So the only way we could change the frequency is we need to change the pitch of the blade. So as the wind speeds up or dies down, the blade pitch needs to change within seconds to keep up with the wind variations. So all times during normal operations, the pitch needs to be constantly moved and monitored based on the wind speed. Okay. If the wind changes in any way, what does the pitch control need to do? It needs to change the blade pitch to keep the speed steady. Okay, so this is has to be a very fine-tuned system so that this mechanical shaft, you can't have, it has to be less than plus or minus by 0.1% error. Okay, so that's a very, very small amount of variations you're allowed on the speed difference. Okay. Now, the other type we can do, this is probably the more popular type, is a variable speed turbine where we'll let the mechanical shaft spin in roughly it'll spin at a certain frequency, but we could give it plus or minus 10 or 20% error. We don't care if it speeds up a little bit today or slows down a little bit tomorrow. It's going to turn a generator. The output of the generator will be variable frequency, but we could use a power electronic system to then clean out the frequency variations and get a nice 60 hertz frequency on the output of the power electronic systems. Okay, so at this point here, it's this AC DC and DC AC conversion right here. This is what fixes the frequency variations. So for variable speed turbine, typically the speed control is accomplished either by the pitch control, which again, turning that blades will roughly change the frequency of the shaft, but we don't have to do it so fast because the power electronics will then be able to change the small, quick errors. So think about pitch control is more just let's do wide sweeping changes, maybe like once an hour, or it doesn't have to be fast. But all the little small frequency variations, like plus or minus 1 or 2%, maybe the wind gusts a little bit, so you have a small small spike in the frequency. Power electronics will figure all that out. Okay, so in this case, pitch control is mainly just to keep the mechanical side in spec, so you're not overspeeding, you're not breaking anything. But it's really the power electronics is a true filter and to fix all your frequency problems. Okay. In very high wind conditions, what does a pitch control need to do? We need to decrease the pitch angle. So if the wind is too fast, faster than what we're designed for, we need to kind of pitch back a little bit to ease off on the power generation, so we're not overloading the generator. We're not spinning faster than we should because the rest of the system can break. Okay. Maybe later on during the day, the speed gets lower, so we don't have that much speed anymore. So we need to increase the pitch angle to keep that rated power. So if we have too much wind, lower that pitch angle for safety. If we don't have enough wind speed, increase that pitch angle. Let's pump up those power numbers to make sure we stay at rated power as much as possible. Okay, until we just can't, we get that critical angle of attack, and then that's about the best we could do. Okay, so that's just the difference in variable speed and constant speed. Again, variable speed is probably the more popular one, especially for the bigger turbines. It's easier to operate, right? Other things we need to talk about pitch control is active versus passive control, right? So active pitch control is basically you have some type of electronic device, maybe hydraulic systems, but whatever it is, it needs constant external power sources, right? So if I want to change the blade pitch, I need to put in some amount of electric energy to even get the system online to start. So that's what active means. So we're going to need power from somewhere, okay? Passive pitch control is when the blade pitch automatically changes on its own power, meaning there's mechanical systems, maybe stored energy in springs, centrifugal forces, but there's some physics involved where we don't have to put electric energy in. We don't have to spend our energy to make the system go. That's what passive means, okay? Another fancier version of this is individual blade pitch control. So typically these first two, when you control the pitch of the blades, it's all the blades have the same pitch. So one controller will control all three blades. So if I want 12 degrees in one blade, the other two blades will also get 12 degrees. A very fancier version is where you have individual pitch control. So one blade could be 12 degrees, another one could be 11, another one could be 13. You can actually have more individual, minute, detailed control, right? Why would you want to do this? Maybe one blade has some balancing issues, so you need to change it a little bit. Another thing is when the blade sweeps on the bottom area, sometimes you're going to hit that the tower is nearby. You might have some wind variation. So when the blade sweeps in the bottom, maybe you could change the pitch a little bit, right? I'll be honest, individual blade pitch control isn't that popular, mainly because the control system is way, way, way more complicated, a lot more expensive. People would end up being into one of these first two. But just want to tell you, it is there. People are thinking about it. Maybe in the future to get that last 1% of efficiency. You know, if we're at 99%, I want to get that 99.9% efficiency. We might have to look at this individual blade pitch control. Okay. So other things for wind turbine control is we need stall protection or stall control. So if you remember, stalling is when you put that blade pitch too much and you go past that critical angle of attack where now there's too much drag, not enough lift, so you're kind of losing power. You went too deep on the angle, okay? So we need to make sure it's like skirting the edge of disaster, because the critical angle of attack is right before when we start stalling. So we want to get all right to that point and then stop. If we get too far, we start stalling. So we'll have an automatic system to when it senses stall condition, it could back off a little bit and we'll get back to that critical attack portion and have the maximum output power. So there are two types of stall control: active stall control, where you have an electronic system that will continuously sense any variations in the power output, a sudden change in the power output. You might have vibration sensors on the blades and the rotor itself, right? There's an easy way you could figure out that you're stalling out. It's a sudden drop in power. You can have more turbulence behind the blade. It's going to start vibrating a lot. So you could sense stall conditions. You'll send a signal to the pitch controller motors to say, hey, we're in stall condition, and the motors will be pre-programmed to back off on the angle, the pitch angle, and maybe reset back to the rated power level. Okay, so this should be an automatic system that will just always work, so you don't have to think about it. But I remember what active means is because electronic system, you need external power. If you don't have external power, then this is not going to work. Okay. For smaller wind turbines, you can do passive stall control where you can still sense stalling based on the vibrations or just, again, centrifugal power forces, power output loss. But there's a passive way we could sense the stall conditions, and then we could use mechanical springs, again, centrifugal forces. Basically, as you spin something faster and faster, you can sense it wants to sling out of the loop. That's centrifugal force. Okay. Those are forces we could use to then power a passive stall control. So think about as we start spinning and we're losing power, maybe there's a spring involved that will activate and will take that pitch blade and bring it back a little bit. Okay. So it's kind of like a balancing act where the spring will be preloaded with enough tension that the blade will always be pitching back and forth right between that critical angle of attack and the stall condition. Okay. That's kind of an automated system, but it's passive because we're not putting electric energy in it. The spring already has the tension inside it. Okay. So good for smaller systems, really, really big systems like the ones you see for wind turbines and utilities. You can't use this because the spring will be too big. Like a spring only has so much force, right? If I wanted a 5 megawatt wind turbine, I can't get a spring to fix that because the spring will be bigger than the wind turbine because it's just too much energy. That's why people like electronic systems, because you can have a very small compact DC motor that produces a lot of power. Okay, but for smaller systems, you might build in the back of your house, in your yard, on a farm. To make it easy, you might have this passive stall control already inside it. Okay. Now let's kind of look at inner workings of each type of pitch control we typically see. First one is mechanical pitch control. We kind of just talked about that. You can see the big spring right here. You can see some levers and some actuators. And you can see this spring is kind of tied to this bolt, which will then turn these blades. So this is the actual blade itself, was the hub to attach it, but the blade will be kind of going out. And you can see the spring will kind of slide in and out. So this thing might have like a plus or minus 10-degree amount of movement just based on this configuration. Okay. So mechanical system can control the blade's pitch by balancing spring tension and centrifugal forces. So for example, if the blade starts spinning too fast, the centrifugal force will want to force something out, and you can have a spring right there to kind of catch it, and then the centrifugal force and the spring can kind of play with each other. And if you have a mechanical system balanced correctly, the forces will balance out exactly at the critical angle of attack, and you'll always be at the optimal range. That's kind of what they're talking about here. Okay. The big advantages for mechanical pitch control obviously requires no external power. Doesn't require electronics. It's typically cheaper because it's easier to get these parts manufactured than like chips and electronics. So the one downside to mechanical pitch control, because it's again the mechanical system, you're gonna need constant maintenance to kind of make sure the spring tensions are there, because springs do wear down over decades. You have lubrication and oil, and these bolts need to be retorqued every couple of years just to make sure they're not getting driven out. So then mechanical systems, you always kind of need to babysit them, right? Every five years or so, we need to check them to make sure everything's in working order. So that's the one downside for that. Electrical pitch control, this is for the bigger wind turbines, right? You need to have to change the pitch, you need to turn the blade at its rotor base. So here you get the main blades. It's literally a turning action right here at the base is where it happens. And what we could do is we could just install electric motor right here. So we have an electric motor that would just then basically move plus or minus 90 degrees. Okay. So an electrical system can control the blade's pitch by either a solenoid piston. So yeah, I said electric motor is probably a solenoid piston rather than the motor itself, right? So basically, a solenoid is literally just one giant cylinder with a giant inductor coil, and then when you're powered on, you're going to push a metal piston in and out. So it's basically action that just moves in and out. Okay, but that's enough to move in and out to spin this blade. Okay, so that's what a solenoid piston is. You extend it out, pull it back in, and you'll get that blade turning mechanism. The big advantage of electrical pitch system is very fast and it's accurate response, because based on if you have a good control and you program it correctly, you can have 1 degree movement almost instantaneously, because I mean electrical systems work very fast. We don't have slow mechanical systems that need to set, reset, and spin about, get up to speed and spin to make things happen. This is why people like electrical systems. Another big thing is there's less maintenance because electronic devices tend to last longer. If you have a controller chip, a Arduino, or a PCB board, you don't need to go every 5 years to do maintenance on it. That thing can last 30 years without even touching it, right? So that's why people like electrical systems. Okay. Another one is hydraulic pitch control, where instead of using electric solenoids, we're going to use literally hydraulics, all right? So to change a pitch, again, remember, you need to turn the rotor base. So again, this is the base right here. You can see the 3 blades. Inside, you can imagine that there's this big cylinder right here, and then you're just pumping fluids in and out. Remember, hydraulic means fluid. So we're going to pump fluid or hydraulic oil inside it, and the piston will move in and out. And as the piston moves in and out, it will turn that blade plus or minus 90 degrees. So turning the blades are done by what we call hydraulic actuators. Okay, same cylinder with a piston that moves in and out, except we're just pumping fluid to push it out. Okay. Typically, blade movement is between 0 degrees to 90 degrees, or a quarter of the base. So the base goes 360 degrees, so we might go from 0 degrees to 90 degrees. Okay. Now, how do you actually control the hydraulics? Honestly, the hydraulic system is probably the most popular one. So this is why we're going to go into more detail. Typical hydraulic system have the following electrical components, right? And hydraulic components. You have a controller, you got a proportional valve. So I'll talk to each one. The controller is literally the microcontroller you program to tell the actuator what to do, how much to go. So this is the brains of the operations. A proportional valve is the fluid will flow into all the actuators. You need to choose how much fluid goes to which one, and you could change the valve. It's kind of like a little screw you could change and direct more flow to the left one, less flow to the right one, and it's kind of like the mechanical control system of the hydraulics lines. Okay, so proportional valve is there to control hydraulic fluid flow. The actuator is kind of the muscle of the system. That's the main piston moving in and out that you're sending the hydraulic fluid to. So the controller tells a proportional valve where the fluid goes. The proportional valve will then send the fluid to the individual actuator. Now, we need the hydraulic fluid needs to be pressurized for this to work. So we need somewhere behind us to have a hydraulic pump to make sure we're constantly putting pressure on the system to make sure it's moving, right? And lastly, we need the actual physical lines or the tubes for the fluid to flow from the proportional valve to the actuator, back to the pump and all that stuff. So it's kind of like the piping everywhere. Okay. So the main parts, controller, proportional valve, those two make the decisions. Actuators and the hydraulic pumps do the physical actions. Okay. Now, this is all, especially the controller, tied to a SCADA controller, right? Supervisor, remember SCADA stands for supervisor control and data acquisition. So SCADA systems typically will run off a 4 milliamp to 20 milliamp range. So you can have wires go to an output device, in this case, a proportional valve, and then you could send the lowest level you could send is 4 milliamps. The highest level you could send is 20 milliamps. And between those two ranges, we could say that, well, 4 milliamp is the 0 degrees, meaning the pitch, there's no pitch at all. And 20 milliamps could be 90 degrees. And we can have a gradient in between. So when we go to 4 to 5 milliamps, 0 degrees will go up a little bit. Then 5 to 6 will go up some more. And then we'll have this 16 milliamp range will be equal to 0 degrees to 90 degrees, right? And we pre-program that. So then the actuator and all the system knows exactly what to do once the time comes for operations. Okay, kind of an image to show you what it will look like. So you'll typically have some type of power supply for the instrumentations and the sensors. You have some type of sensor right here because you need to know what the pitch is, the current pitch angle is. You also probably want to have some information on like the weather, the wind direction, all that. So there's a bunch of sensors that you'll power up, and then the power then go to the actual controller. So right here you have a controller and you got your little pin outs, and you'll literally take a little resistor right here, and then the current will flow. You have some voltage across here, and you can plug it into your SCADA controller, and it'll read that like maybe 20 volts or 10 volts, and that will be some range for you. Okay, so this is the sensing side, and then you can also output for another 2 pins, either 4 to 20 milliamp, and that could go to the after hydraulic system as well. So SCADA systems, this 4 20 milliamp loop, this is very common in all of power systems, so you're probably going to see this again. Okay, here's a very unique question. Why do we use 4 milliamps instead of 0 milliamps as the lowest value? Wouldn't it be easier if this is 0 milliamps to 0 degrees and 20 milliamps to 90 degrees? Math-wise, it would. But somebody a long time ago said, how can we tell if something's offline and actually 0? Right? Because 0 means nothing in terms of changing a system, but we're still online sending that 0 signal, right? So if I use 0 milliamps for 0 degrees, when I turn off the system, the blade pitch still thinks we should go to 0 degrees. And that's wrong because the system's completely offline, right? So a good fail-safe mechanic or a safety system is, let's make 0 a very small value, so when troubleshooting time comes, we'll know if the system's offline or online. Okay, so we differentiate 0 value of 4 milliamp versus a broken system, which is 0 milliamps. That's a big difference. Okay, and a lot of electrical engineers like this. If you ever go to EEE 194 or any of your digital logic systems, you notice that 0 is not 0 volts, right? 1 is like 5 volts. 0 is like 1.3 volts or 0.3. I forgot what it is, like 1 or 1.5 volts, right? It's the same logic. We don't want a binary 0 to be actual 0 because then the circuit will be off and you would trick the system. Okay. So 4 milliamp, 20 milliamp loop, very, very common. So let's do some math just to show you how you will parse out a instrumentation sensor. So let's say you have a sensor and you need to program the SCADA controller. Well, you need to tell the SCADA controller what's 4 milliamp mean, what's 20 milliamp means, and what does everything in the middle mean. Okay, so this is you programming the controller. So at the lowest level, where pitch equals 0, we know we're going to have 4 milliamp. At 90 degrees, that's the maximum, we could put 20 milliamps. So we got to program the min and the max. And then we need to program the rate in between. Okay? Now we can figure it out. So the question is, what will be 45 degree pitch? The mid right in between these two, what's my current value? Well, it's not as simple as taking 20 divided by 2 or 4 multiplied by 2, right? There's some level in between. We kind of need to map it out, right? So it's kind of called sensor mapping. So let's do some logic. We know 45 degrees is halfway between 0 and 90 degrees. So therefore, 45 degrees will be halfway between 4 milliamp and 20 milliamp. Okay. Now, first we need to figure out the range between these two. If I take 20 milliamp and minus 4 milliamp, I know my range from smallest to largest is actually 16 milliamps. Okay. This gets a little confusing to people. They think it's 20. It's not. It's actually 16. Okay. So let's take 16 milliamps and let's take half of that because that'll be the halfway between 4 and 20, which we said right here. So half of 16 is 8 milliamp. That's exactly at the 50% range. So at first people say, well, I should put 8 milliamp here. That's wrong because you still got to put that 4 milliamp at the 0 value. Okay, so you see 45 degrees will be the 0 degrees of 4 milliamps plus the 50% range of 8 milliamps. So you actually will get 12 milliamps. So the correct answer at a 45 degree pitch is 12 milliamp, not 8. All right. So it's kind of a little confusing, but this is, you just got to remember that 0 in our case is not 0 milliamps, it's actually 4 milliamps, and you have to count up from there. Okay. So a very simple problem, but I just want to show you this range variation. And this is very typical mapping you would do. Now, let's go to the next level. Right? How many milliamps are needed to move the blade by 1 degree increment? That's another thing you're in program. If I want to move by 1 degrees, how much current do I need to increase? All right. So I know 0 degrees to 90 degrees has a 90 degree range. I know my range on my SCADA system between 4 milliamps to 20 milliamp is 16 milliamp range. So 1 degrees multiplied into the range is 16 milliamps over 90 degrees because this is the ratio to full range, means each degree is 0.178 milliamp increase. So you have to program that into your SCADA program, PLC or whatever Arduino board you're doing, that it is a linear increase of 0.78 milliamps per 1 degree. Okay. Now we have everything included. Can I calculate what's my current value in milliamps? We need to have the blade pitched at 30 degrees. So let's say we want to pitch the blade at 30 degrees. What does my controller do? How much current does it send out? Okay. Well, 30 degrees, well, we know 1 degree is 0.178. We could multiply this together. 30 degrees times 0.178 milliamp divided by 1 degree. Degrees cancel. I'll get 5.33 milliamp. And again, people think this is the answer, but no, don't forget. That's going from 0 degrees to 30 degrees. We still need to add the base value of 0 degrees, which is 4 milliamps. So adding these together, we're actually about 9.33 milliamps. That's what the controller truly needs to send out. Okay. And we could kind of do some rough verification. Is 30 degrees is equal to 9.33 milliamps. Go back over here. 45 degrees was equal to 12. So you're not too far off in the middle because 30 degrees and 45 degrees aren't that far off, right? So the numbers kind of check out. For example, if I only put 5.33 and I looked over here and I saw 0 degrees is 4 and 45 degrees is 12, that immediately tell me something's wrong because 5.33 is much closer to 4 than it is to 12. I should have 5.33 is really like 10 degrees. Okay. So it's just a good, kind of do a little of a head check of do these numbers make sense or not, right? That's a good starting point for checking your answers. Okay. All right. With that being said, I want you to go through the whole system we just did here. Tell me what current is needed from the skater controller to set the blade pitch at 40 degrees. So you calculate that. Secondly, if we want to go from 40 degrees to 75 degrees, so I want to increase the pitch, how much is what increase does the skater controller need to contribute? So if I'm at 3 million, let's say I'm at 8 milliamps, and I want to go from 40 degrees to 75 degrees, how much additional current do I need on top of the 8 milliamp? So you figure that out. Okay. We'll come back in 15, 20 minutes and check your answers. Let me know if you have any questions. Otherwise, good luck. See you in a little bit. All right, hello everybody. Welcome back to EEE 135, Chapter 8, Wind Turbine Control. So we just talked about having an exercise on the hydraulic skater controller. So let's go see how we can calculate our current. So first thing, we have 40 degrees, we need to move the pitch blade to 40 degrees. I know 0.178 milliamps is 1 degree, so you just multiply 3, you get 7.12 milliamp, plus the 4 milliamp from the base 0 degree starting. So our total current going to the control from the controller to the proportional valve is 11.12 milliamp. Okay. Part number 2 is we want to then change from 75 degrees up to 40 degrees, or from 40 degrees up to 75 degrees. So we need to add a 35 degree addition. So here we got 35 degrees multiplied 0.178 milliamp. So we just have to increase by 6.23 milliamps, right? Notice we didn't add 4 milliamps this time because we're already started at 40, we're going to 75, so the 4 milliamp was already accounted for, okay? So here we will just take this previous value of 11.12, then add 6.23, and then that will be your total current would send to the controller, okay? So that's your kind of little basics to SCADA controllers. So we're going to shift gears now. We're going to talk about yaw control. So everything previous was pitch control. So remember that the wind turbine needs to face the wind direction to induce the optimal power. So we always make sure wind turbine is facing directly into the wind, the blowing direction. We can accomplish this by turning the whole entire body, right? So here we have pitch control, and kind of draw this in, right? Yaw control will be if we're moving it this way, like so. Okay, so that will be yaw control. Okay. So it kind of says it right here. Everything is inside it, and then the actual body is turning 360 degrees around the base of the tower. Okay. This is called yaw control, and again, another very important part of the wind turbine control system. Two types of yaw control we can use. First one is called passive yaw control. And then again, this has been around for probably thousands of years. Is people a long time ago got smart and realized if we put a large tail at the end of the wind turbine far enough, when the wind blows, it'll hit the tail and naturally turn the whole wind turbine into the wind. Okay, so a large tail behind the wind turbine that can the wind turbine can rotate. The wind turbine itself can rotate 360 degrees. When the wind blows, naturally it's going to want to make sure the tail is parallel to the wind blowing direction, so there's less resistance. All right, so it's a naturally self-aligning unit. What would happen if wind direction suddenly changes? The wind will blow in the tail and then turn the wind turbine back into the direction. Now, you got to remember the tail has to be pretty far behind the wind turbine, mainly so that it gets enough torque to actually spin the whole thing. Because it'll be a little bit hard to spin the wind turbine itself because the blades are already moving. Okay, so every tail has a good, like, I don't know, this could be like 3 feet, 6 feet behind, okay, the wind turbine itself. Next, we have active yaw control. This is probably for the bigger wind turbines that a tail, the tail you can't use for like a 5 megawatt turbine because the tail will be the size of a building itself to create the torque needed. So instead, we use an electronic system. We use active yaw control where we have these DC motors right here. So they're very high torque, slow moving DC motors combined with a gearing system. And here, these gears will spin around the tooth of this large gear and spin the whole body around. Okay. So here you need the DC high torque motors and gearing systems. You also need a controller to tell the motors how long to turn on. You also need wind sensors to know the direction of the wind so we could tell what direction we need to face. Okay. We also need external power to feed this whole system because motors don't turn on their own and they take a decent amount of energy. Granted, yaw control is not needed all the time. Typically, wind direction doesn't drastically change every 10 minutes. It's pretty calm. It will change throughout the day, but not instantly. So pitch control is very like real-time, quick in seconds. Yaw control can take a little bit longer, right? And also you might only use it like maybe 2 or 3 times a day. Okay. So you need external power. It's pretty beefy, but you're not going to need a lot of it. Okay. Typically, where can you get external power from? You either get it directly from the grid or a battery system nearby. Okay. So kind of little details of the electrical system on its own. You got the main gearing system. This yaw ring gear ring, this is attached to the tower itself. It does not move. And then the motors will move in a circular motion around the base gear ring. And then that's what spins the whole body itself. So the yaw motors are typically going to be attached to the body. Okay. Let's see what it says up there. Yeah. Yes. Yeah, you can see right there. It's attached to the body. Yep. What are the characteristics of the motors that we use for yaw control? They need to be very high torque because this is a lot of weight to move. It needs to be low. It can be low speed application because if you remember back for DC motor sections, if you want high torque, it has to be low speed. If it's high speed, it must be low torque. So they're kind of inverse of each other. So I will accept low speed operations. If it takes 10 minutes or 5 minutes or 10 minutes to do a 180-degree turn, I'm fine with that. It's not that big of a deal, right? But we definitely need a high torque to get it moving. It needs to be a very compact design because it needs to fit within the body of the wind turbine itself. And we ideally want it to be low maintenance because we don't want to have to go up there every year and change things out. So again, this is a big item for long-term costs. How do we power these devices? You're going to have DC power. You can either get that from the power electronic systems inside the body itself or a separate external source. We typically call this station service or auxiliary service. This could be a separate substation or a separate power electronic unit where it is constantly putting DC power to all the wind turbines in the farm. Okay. So electric yaw control, by far the more popular one. Now you have the control loop itself we'll have to take a look at. So here is your logic controller. The input to the control system will always be the actual wind direction. And so you have a wind vane that will tell you what direction the wind is blowing from. And then we need to know the current position of the actual wind turbine itself. So there's going to be a little sensor at the base, and it'll say, hey, we're 20 degrees to the right or 40 degrees to the left, and then we need to turn additional 10 degrees or 20 degrees. That's what the controller is going to make a decision on. It's going to say current position plus the new ideal position from the wind vane, and it'll figure out the difference, and it'll send a torque request to the actual yaw motors and actuators, and that will physically turn the actual wind turbine. So what's the input? Wind direction, position in the wind turbine itself. What's the output? Is the signal to start the motor, the torque level needed, and how long do we want it? We want to do it for 2 seconds, 5 seconds, 10 seconds, depends how far we need to travel. So it's a basic, very basic standard feedback loop system. Okay. Now another issue we'll have is the yaw rotation. So the yaw rotation can be 360 degrees because I mean, there'll be times maybe the wind blows in opposite direction, maybe. So the thing will have to spin all the way around to catch the wind. Okay. So the yaw motor is going to turn, but remember, all the power is up here. It needs to eventually go to the base of the tower to go to the main power grid. So there needs to be giant cables that connect the generator and power electronic devices upstairs to the base ground level. And this is called the tower cables. And one issue we have is if we spin the turbine too much, we're going to start twisting the cables. They're going to get kind of twisted and bundled up too many times. You might snap them. So we need to make sure this doesn't happen. So say if we keep turning clockwise, tower cables will twist too much and possibly break. We have to design a system to circumvent that. So one is to just have a lot of slack in the cables. You can see how it's kind of like there's a bracket here, and then it's falling down from the actual body, and there's probably a good 3 feet of play for that. That way you could twist it a bunch. But there's only so many times you could twist it. So you could have cable slack and have a rotation counter. Once it senses that it rotated maybe 10 times, it's going to lock that direction and then make the controller force the wind turbine to start unwinding in the opposite direction until we get to maybe something net zero twists, something like this. Okay. Another option is to just not deal with cables and use slip rings instead. Same slip rings we've seen with synchronous motors. We'll use it here, or synchronous generators. Okay. So the cable part, that's pretty obvious, but the slip ring might be not so obvious. So let's take a page on that. So here, notice at the bottom of, you have the actual body itself. You have the main cables come out. It's going to go and connect to these metal cylinders, right? You see these kind of yellow branded cylinders. These are all the main cables from the actual body, right? And then you'll have these brushes right here that will connect cables down to the bottom like so. So you have some cables that come in, gets welded to the contacts, and then the brushes touch the contacts, and they transmit energy, and they go down to the base of the tower. The nice thing here is these are not welded together, so they could literally spin infinite amount of times, and the brushes will always stay in contact with the actual ring itself. Right. So you slip rings. The big advantage is not affected by number of rotations in the turbine body. You can literally spin as many times as you want. So it's an easier control system, less complication, one less variable you need to think of. The slip rings do come with one big caveat and disadvantage. It's one more maintenance item you need to keep track of. Remember, maintenance in wind turbine is a bane of all existence because you have to go up there. It's a lot of work. So slip rings, I mean, these are little friction pads. They wear out. If you spin this enough times, these have to be replaced. They at least need to be inspected probably every 5 to 10 years. So this is, again, one more problem that we have to deal with. It's a long-term problem we have to deal with. So it's kind of give or take. Some people use this. Some people use a simpler, just put cable slack. It's cheaper. So it's really up to you what you want to do. Okay. So in summary for today, we talked about pitch control. Remember, pitch gives us the angle of attack. It also is in charge of how much mechanical power we can harness from the wind. We can get that critical angle of attack to maximize the power and the speed, right? If we have too much speed, we could pitch really hard, go into stall condition on purpose, slow things down, right? Or if the wind is too slow, we have to increase our pitch to pick up more energy. Okay. Several types of pitch control systems we see in today's wind turbines: and mechanical pitch control, electrical pitch control, and hydraulic pitch control. Probably hydraulic being the more popular ones for the large wind turbines. Next, you have yaw control. This controls the direction the wind turbine is facing. To follow wind direction changes, you always want to follow the wind direction. So if it changes a little bit, you change with it. Okay? The type of pitch control systems typically we use is very simple, a tail on the wind turbine. This is a passive mechanical system. Or more for bigger wind turbines, you must use a separate electrical yaw control system with DC motors, external power controllers, and all that jazz put together. Okay. So that's all I have for today for the wind power control systems. Thank you for showing up. Learn a little about SCADA system as well. We'll come back next week and we'll talk more about the internal control systems, mechanical systems inside the wind turbine body itself. Okay. So hope you guys have a good rest of the week, next couple of days. Catch you later on this week for the next video. See you around.